share your screen. Very good. Okay, so yes, the floor is yours, Niklas.
Okay. Yeah, thanks very much. And thanks to the organizers for putting together this nice meeting and for the invitation. I'll present a work that's a bit older, but so this was with Massimiliano Gubinelli from like 2 or 3 years ago, although it was published this year. And but there are some new contributions by Lukas Gräfner's master thesis, who's now a PhD student with me. And yeah, so in the beginning, I'll explain this part, and then I'll explain the new contributions by Lukas towards the end. And the goal is to understand whether we can get probabilistic theories for the kind of equations we would solve in regularity structures. So at the end, we will formulate a singular Martingale problem for some. I mean, I will just focus on one example, but it works for a few cases of singular SPDEs, and we will construct the infinitesimal generators. And I like this program. I've been working on this for a few years because you can combine many different aspects of math in there. So we need some rough path ideas, regularity structure type ideas, but the techniques are not really there, but the ideas from that field, we combine that with Martingale methods, Gaussian analysis, infinite dimensional analysis, and this is more recently, there's also a lot of functional analysis coming in. And this kind of theories then are useful, for example, and this is why they were invented, I will get to that, for proving scaling limits. But for example, if you have the generator, I mean, generally, what is the generator good for? You can understand ergodicity of your process from that. You can prove functional inequalities or fluctuations of your process are also studied like that, or moments can be well described in this setting, and moments are not so easy to describe in this pathwise regime. Let's see. So the main example, somehow I have to, sorry. Yeah, I have to get rid of these videos because they're blocking my screen. Of this, yeah, okay, sorry. So the main example we have in mind is the derivative of the KPZ equation. So we will focus on this on the one-dimensional torus. We could do the same thing on R, but for simplicity, let's take the torus here. And so this is this equation here. So we have the heat equation, then we have the derivative of a space-time white noise. Because in the KPZ equation, you would see the space-time white noise. So once we take the derivative acts on the noise. And then we have the nonlinearity here and the derivative also acting on the nonlinearity of the U square. And okay, this is this usual story in this business that we cannot make sense of the equation somehow classically because U square would be the square of a distribution. And we have a problem with that, because the invariant measure of this SPDE is the white noise, so it would be like the square of the white noise. And we can, of course, for quite some years now, solve this equation actually. So we know how to overcome this problem, and this is based on pathwise arguments. And the idea, for example, in regularity structures would be we freeze the realization of the noise, and after that we only argue for one fixed omega, and we do a sort of generalized Taylor expansion of the solution, where here we have these generalized monomials, and then we have a term which at least morally behaves like x minus y to the gamma, and gamma can be anything we want. We can choose gamma to be 5 or like, I think 3.5 maybe in this case would suffice, but you could do it up to order 10 if you wanted to. And so in that sense, the solution is actually a smooth function of the noise, right? And at least in terms of these generalized monomials, and with this thing interpreted in a generalized sense. And well, since it is a smooth function, then you could somehow imagine that you can make sense of such nonlinear operations, and this comes down to understanding the nonlinear operations on the trees. Okay, because it will be relevant later, let's talk about how far we can go with this theory with regularity structures. And essentially this works for locally subcritical equations. So you need some other conditions on top of local subcriticality, but essentially local subcriticality is the main thing you need. And what does local subcriticality mean? So let's look at such an equation here. A is now some operator, xi is some noise, doesn't have to be white noise or Laplacian, and f here is a nonlinearity. Then we say this equation is locally subcritical if there exist scaling exponents alpha, beta, gamma, such that if we scale space by lambda, and ultimately we're interested in understanding what's happening on small scales because we want to understand regularity. So we want to send lambda to 0. So we zoom into the small spatial scales, and then we also want to zoom into the small time scales, which means the beta here should be positive as well. So we do space-time scaling like this. For example, if A would be the Laplacian, the beta should be 2 here, because then this will be the parabolic scaling induced from the Laplacian. And then we multiply with some lambda to the alpha. Alpha can be anything at once. And then this rescaled element should solve this equation here, where now here we have the same thing. Here we have a noise, which is not the same noise, but the law of this rescaled noise is the same as the law of the original noise. And then here we have lambda to the gamma in front of the nonlinearity. And gamma should be positive. So this is the subcriticality condition, that the gamma here is positive, so that if we send now lambda to 0, this term formally drops out. So we can interpret the solution as a perturbation of a linear equation in some sense, right? Because for small lambda, this thing here is not important. And if gamma is equal to 0, then the equation would be formally scaling invariant and therefore critical. And somehow this then does not work in this setting anymore. And if gamma is less than 0, then the equation would be supercritical and we would actually blow up the nonlinearity. So it would somewhat dominate on small scales. Okay, now let's look at what we can do for STEs, what kind of solution theories we have there. So if we want to solve this equation, the first way of solving that we learn in our stochastic analysis class is that we can find a strong Ito solution. So we fix the Brownian motion and we find a process which is adapted to the filtration generated by this Brownian motion, and we interpret this thing as an Ito integral. The next thing is the weak Ito solution, which as a student is maybe a bit more difficult to grasp what's going on there. So the key point there is that the solution doesn't have to be adapted to the Brownian motion, and there may be additional randomness needed. And what's important here is that this weak solution is equivalent to the Martingale problem. I will briefly discuss the Martingale problem on a later slide. And then we have the rough path solution, where we freeze the realization of the noise, make sense of this integral pathwise, path by path, as a rough path integral, and then we solve for each fixed omega. And in this case, for example, the solution depends continuously on the noise in a suitable rough path topology. And so each of these approaches has different strengths and weaknesses, and depending which problem you want to tackle, it would be better to use, well, either rough path or weak or strong Ito kind of solutions. But now for singular SPDEs, like this Burger's equation, we only basically have this last approach. And so the goal that I would generally like to understand is whether we can make sense of 1 and 2 as well in this setting. And yeah, so just quickly, because I mentioned the Martingale problem here, let's just quickly recap so we're on the same page. So if we have such a diffusion, the Martingale problem just means we apply Ito's formula to a nice test function, and then by Ito's formula here we get some differential operator acting on phi, and here we get a Martingale. This L of phi, yeah, is the generator of the SDE. And so we know that phi of xt minus phi of x minus this drift here, where we just see the differential operator acting on phi, becomes a Martingale. And this characterizes the law of the process uniquely, at least if things are sufficiently nice. And so therefore we have a description of the law of this diffusion through a differential operator. And yeah, this can be used for various things. Good, so now let's try to do the same thing for Burger's equation. So this was the singular SPDE here. And let's take a test function. We have to basically, I mean, okay, I didn't really say what it means to be a solution, but let's ignore that. Let's say we have a solution and let's try to see how the Martingale problem should look like. And we should then apply a nice function to the solution and apply Ito's formula and see what we get. No? And the nicest, so the solution to this equation will be a distribution in the space variable. The nicest function I can think of that you can define for a distribution is just testing this distribution against the C infinity function f. So let's do that. So just a linear test function. And then we get, okay, there's a question in the SDE setting with Brownian motion noise. Is the rough path approach equivalent to the strong solution approach? In the case where both apply, yes. So if you have sufficient regularity and good boundedness condition, I mean, somehow the right boundedness condition on the coefficients, then the two will be the same, yes. Like this. Okay, sorry. Okay, so we have this linear testing and we apply Ito's formula, and then, well, here we have this guy. So this we just integrate by parts, the derivative. And then we integrate this derivative by parts. That's as well, no problem. And this gives us a plus, the plus becomes a minus. This gives us a minus. And then this part, okay, you can write out what this is, but let's just say this will be the Martingale. So this here is the Gaussian, I mean, derivative of space-time white noise, and somehow then integrating this in time will give you a Gaussian Martingale. Of which you know everything here. Okay, so the generator should be just this thing here, right? For this phi, the generator should be this function here. But the problem is that the state space is a space of distribution, so h minus 1/2 minus epsilon, this Sobolev space would be okay. But on this Sobolev space, of course, u squared is not defined. I cannot square general elements of h minus 1/2. And so therefore, the generator is defined for general elements of the state space. What we could hope for is to construct the generator not for all u in the state space, but maybe somehow for almost all u. And for this, we should say, of course, almost all with respect to which measure. Well, then we should take the invariant measure of the equation, and the equation is invariant under the law of the white noise. So we could hope to do something like that, but for general u from the state space, it will never work. Before we get to that, we will do something like that, except that we will also have to change. So we will define something like this, except that we will not take such a phi here, but we have to take some more complicated phis. But this we will do. But before we get there, there's something else that we can do that I want to briefly mention. This was somehow done previously to this what I'm discussing now, and these are energy solutions. So they were invented by Patricia Gonçalves and Milton Hara in 2010, actually. Some of this was then published in 2014. And then Gubinelli Hara added additional conditions to the definition of energy solutions that made it easier to work with them. And then a few years later, we proved that these somehow finer, with more conditions, energy solutions are unique. We have pathwise uniqueness for them. So what are energy solutions? Basically, okay, so the first thing is we're going to assume that the law of the solution is absolutely continuous with respect to the formal invariant measure for all times. Then there are some additional technical conditions. And using these technical conditions, and this was somehow observed in these works, we can make sense of the generator if we're not too greedy. So if we say, well, let's not try to make sense of L phi of u, but let's just try to make sense of this time integral. And it turns out that this works with these technical conditions. And based on that, you can define energy solutions, which is basically somehow like a weak solution to this equation, plus some additional technical conditions mentioned here above or hinted to here above. And yeah, the strong well-posedness of such energy solutions we can then prove through the Kohl-Hopf transformation. So we can prove a very special, somehow restrictive, but sufficiently general sort of Ito type formula for the solution to this equation. And based on this Ito type formula, we can do a transformation by which we can linearize the equation. And then the linear equation has pathwise uniqueness, and then the transformation is invertible, so we can go back and get pathwise uniqueness for this equation. That's the general idea. What remained open, so this was this work from a few years ago, what remained open there is to construct the generator really, L phi of ut at a fixed time. And really this is different, significantly different. So to understand this, let's look at a very simple example. Let's just think of a Brownian motion and the Dirac delta. This integral here is perfectly well defined for the Brownian motion, and it's just the local time of the Brownian motion, the Dirac delta of the Brownian motion at 0. And somehow it's not so complicated to construct it, but the Brownian motion, I mean, the Dirac delta of BT itself, that's not something we can really make sense of, because this would either be 0 or infinity, somehow depending on whether the Brownian motion sits in 0, and it's not really something that we can work with. And so now here we have this integral, but what we would like also to understand is what happens at a fixed time. And of course, somehow this transformation which linearizes the equation is really dependent on everything in this here. No, it has to have exactly this form. If we change the operator here, or do something with a nonlinearity, or we go to some other equation, like later I'll mention some fluid dynamic equations which somehow have a similar structure, but in all these cases we cannot do this transformation. So can we find the question is, can we find an approach which is more robust? And so we can, but we go from pathwise uniqueness to weak uniqueness, to uniqueness in law. This is what we have to sacrifice, because now we will only argue for the Martingale problem. So let's see how the generator looks like. And let's say we take general nice test functions phi. Let's look at an SDE first here, such a simple SDE with additive noise. Then the generator would be just somehow B inner product with the gradient of phi, first order operator coming from the drift. And this we can write as sum over the coordinates, B kth coordinate, and then derivative in the direction k. And then plus 1/2 times the Laplacian, which is coming from the noise here. Now for Berger's equation, we have, well, this part here, I will just write as L0. This will contain something like a Laplacian, and then the contribution of this part here. And it turns out that these two work very nicely together. And this L0 operator will be very nice, we'll see that. And then we have the contribution from this part. And this, by analogy with a finite dimensional setting, should be the sum of all coordinates and then derivative in the kth coordinate, where Ek here is an orthonormal basis of L2 over the torus. And yeah, so this operator we call G, and D here, okay, so the Maillard derivative, or you can just think of it as the Fréchet derivative in the direction Ek. It's somehow the same thing. Okay, so the idea, the problem with this is that it still contains this derivative of u squared here. Somehow things are still very singular. And if we take a nice phi here, then we don't get anything that really makes sense. So the idea to get a phi for which L of phi is well defined is to somehow construct, or the idea is to construct very special phis for which we can make sure that this thing here is a nice function and not something so degenerate as this thing here on the right hand side. And one way of doing this, which is somehow coming from these works, Flandoli-Rousseau-Wolf, de la Rudière, and others in this setting, which are considering finite dimensional SDEs with distributional drift. And it turns out that this here is something like an infinite dimensional SDE with a distributional drift, if you think about it in the right way, is to solve the resultant equation. So we solve this equation here. And then automatically, if we have the solution to this equation and we have a bit of regularity for the solution, then automatically L of phi will be lambda phi minus psi. Psi we choose, so we can make sure that this is a nice function. And lambda phi, if we have a regularity theory for it, will also be a nice function. So this is an infinite dimensional PDE. We have to make sense of what regularity here even means, right? It's an equation on this infinite dimensional space. How do you measure regularity on this infinite dimensional space? What reference measure do we take and what function spaces do we take? And of course, the reference measure will be, again, the law of the white noise. And then based on this, we will define suitable function spaces. Okay, so the white noise, now I can formally define it for the first time. So this is the centered Gaussian measure indexed by test functions such that U of f somehow, I mean, this is a Gaussian process if f runs to all test functions and the covariance is just the L2 inner product. And then so there's the chaos decomposition, which allows us, and this is really the main tool in the following analysis, which allows us to identify L2 of mu. Mu is the law of the white noise, so L2 with respect to the law of the white noise. So now we have a measure on our infinite dimensional space and we have a function space. The most basic function space is L2. And now we can identify this function space with a sort of Fourier transform, which is just the chaos decomposition, right? So the Fourier transform allows you to identify an L2 Lebesgue space with a sequence of numbers. So you go somehow from a function space to a sequence of numbers. Here we go from an infinite dimensional function space to a sequence of finite dimensional function spaces. And what is the sequence of finite dimensional function spaces? Well, this is the Fock space. So infinite direct sum of L2 over the n-dimensional torus. So the nth factor here has the n-dimensional torus as an input. And the only difference, the only subtlety is that we have to take symmetric functions. So we look at functions which are symmetric, so functions of n arguments, and their value should not change if we replace two of the arguments. And so there's an isometry between this space and this Fock space, and any element in this space can be identified with this with a sequence, and then the inner product on the Fock space is this weighted sum of L2 inner products. And now basically what we could do if we really want to do a sort of Fourier transform is then apply the Fourier transform on each of these terms here. And in this way, we would have identified these infinite dimensional function spaces. So any element in this infinite dimensional function space would then correspond to a double sequence of numbers, because then any element here can be identified with a sequence of numbers. Okay, now we want to define more sophisticated function spaces, and we will from now on then only work with this Fock space. So we go over through the isometry to the other side, to the Fock space side, and now we do analysis there. And to measure regularity, we define two operators and then define function spaces as domains of these operators, basically. So the first operator is the generator of the heat equation. There we just so this L0 is the same operator L0 that we saw before, is the generator of the Burger's equation without nonlinearity, so just of the stochastic heat equation. So if we remove the nonlinearity, then the generator will be this L0. And this is just acting on somehow such a sequence of functions. It just takes the nth function for each n and applies the n-dimensional Laplacian to it. Yeah, so somehow, yeah. So this is basically just like Laplacian in this setting. And then we have the number operator, which, so this here measures the regularity of the kernels in this expansion. And this operator here measures the size of the kernels. So it's just multiplying the nth kernel with n. And based on this, we then define function spaces. So for example, H alpha beta would be the domain of 1 plus n, 1 minus L0, 1 plus n to the beta, 1 minus L0 to the alpha. So the 1 minus is just somehow to avoid problems with taking negative beta and alpha here. So that don't really, yeah. I mean, in principle, these operators have 0 eigenvalues, right? And then, of course, you cannot invert the operator. So by putting 1 minus the operator, we can make sure that we can really invert it. And of course, somehow, if these things are negative, if one of the two is negative, then the space should, I mean, then the domain would be in principle all of L2, if both of them are negative, let's say. But then we don't mean that H alpha beta should just be L2, but then we take the closure of the domain with respect to the induced model. So basically, these are all sequences of generalized functions such that the norm induced from this thing here is finite. Yeah, and so this leads to nice functions, so somehow to notions of smooth functions. If alpha and beta are positive, then this means I'm not just asking that these guys are in L2 and that this sum here is finite, but I'm even multiplying this with additional powers of n. And here I'm not just taking the L2 norm, but I'm taking somehow stronger Sobolev norms. This is what we get if alpha and beta are positive. But if alpha and beta are negative, then it might be that the kernels are not even in L2, for example, or that this sum here is infinite and it only becomes finite if we additionally dampen it. And the point is that this identification, I mean, this Fock space is only a construct with which we do calculations. And going back to the world of random variables is only possible if both indices here are positive. If one of the indices is negative, we are somehow on a level on the Fock space which has no correspondence in the world of random variables. Basically, that would be something like a distribution in omega, which you cannot evaluate for each omega, but you can only average over omega by after multiplying with a smooth random variable. So something very weird. It's something which doesn't make a lot of physical sense, but it's a good tool for computations. And we can work with that. And at the end of the day, whenever we go back to stochastic processes, we just have to make sure that here we have positive regularity. Okay. So now we have this operator here, which we can write as L0 plus G. L0, remember, was the Laplacian in each coordinate. This is just the generator of the linear dynamics here. And G is the singular part coming from this thing. Now we can do regularity estimates now that we have function spaces, and you can check. Basically, the precise formulation is a bit more complicated, but basically morally something like the following. So G of phi loses 3/4 regularity in space. So this is the regularity with respect to L0, the upper index, and 1 degree of regularity with respect to n compared to the input. So this a priori seems more or less nice because, well, we have also this L0 here through which we could hope to gain 1 degree of regularity in the upper variable. Okay, no, that was not the point that I wanted to make. That okay, sorry. This seems okay in principle. Then you would think I'm just taking phi of very high regularity. So I take alpha bigger than 3/4, beta bigger than 1, and then I get a nice function here, right? But this does not work. So no matter how smooth phi is, even if it's like an H infinity, we cannot make use of its spatial regularity here. We can only make use of regularity 1/2. And since we lose 3/4, the output will always have negative regularity. So it will never be a random variable. It will always be such a weird distribution. And then this idea so for smooth functions, we can never hope that they're in the domain of the operator, because if I plug in a smooth function, then this thing here will again be a nice function, but this thing can only be a distribution for a smooth function. And so the idea, which is similar to the idea, for example, used in the construction of the Anderson-Hamiltonian or other singular operators, is to find a domain of non-smooth functions such that, well, this thing here will still be a distribution, but maybe this thing will also be a distribution. And maybe the distributional parts of these two can cancel exactly, and the remaining part maybe will be a nice function. And to do this, we want to solve the resolvent equation. And well, this is the resolvent equation. And if we write it in terms of L0 and G, it comes down to this. So we have to write phi is equal to lambda minus L0 inverse of G phi plus psi. Now, if we would like to do a Picard iteration for that, we somehow have to show that if we plug something into this map, we remain in the same space. But then there's a problem because inverting this, okay, gives me back 1 degree of regularity. Well, here I lose 3/4, so that's fine. But here I also lose in the lower variable, lose this beta -1 from beta, but inverting this thing only gains in the upper variable. And this is somehow a key difficulty. However, we have a bit of regularity in the upper variable even left because we gain 1 and we only lose 3/4. So we have 1/4 to spare. And so the question would be, can we trade off between these two? And this we can do by projecting to the large Fourier modes somehow. So we do spectral calculus, but you can write down explicitly what this means in terms of Fourier coordinates. So this pi upper projection operator goes to the regime where 1 minus L0 is bigger than 1 plus n to the 4. And why 4? Well, this is related to the fact that we have 1/4 derivative later to spare. So let's see what kind of estimates we can get for this pi upper. So we want to gain 1 degree of regularity in the lower notion of regularity. So we write down the definition of this. It's 1 minus L0 to the alpha, 1 plus n to the beta plus 1, and then this indicator function here. And since 1 plus n to the 4 is less than 1 minus L0, we can just trade this plus 1 here against the 1 minus L0 to the 1/4. And then we throw this over here, leave this part untouched, and so we get that we can bound this part here by this part here. So we can trade the quarter derivative in the upper regularity for 1 degree of regularity in the lower regularity, if we have this pi upper operator. Otherwise, of course, not. And based on that, okay, so if you plug in the estimates together, it's, okay, I'm going a bit quicker now. It's not difficult to see that you can solve this modified resolvent equation where the G on the right-hand side is replaced by G upper. And actually then, because we threw away the large Fourier, the small Fourier modes, there's no need anymore to take lambda here. We might as well take lambda equal to 0. And we can solve the resolvent equation in that case. And this gives rise to the notion of controlled functions. So these are solutions to resolvent equations where G is replaced by G upper. And okay, the first thing is we can show that these controlled phi exist and are dense. We will not comment on that. The second point is that these controlled phis are actually in the domain of our operator. So we have found a domain for our operator. And how do we do that? Well, let's apply L to phi. Then we split L into L0 and G. And in the L0 part, we plug in this controlled form of phi. So using that phi solves a sort of resolvent equation. Then we get L0 of phi sharp, but phi sharp is something we choose. And so we can choose phi sharp to be such that it is in the domain of L0. That's fine. And then here, these two give us a minus G upper of phi, but here we have a plus G of phi. So the G upper parts cancel and the G lower part here remains. And so this here is like G of 5, except that we project it after applying G, we project it to small frequencies. And the reason why this was a distribution was coming from large frequencies. So after we removed the small frequencies, the large frequencies, there's no more divergence and the thing becomes like a nice function. Okay, based on that, this was really the main part. After that, we can prove that we have existence of solutions to the Martingale problem. This goes through Galerkin approximation. There's a lot of technical computations necessary there, but somehow it's all as you would expect it to happen. Somehow you do everything like you would expect to have to do it, and that works. And for proving uniqueness, we use the duality of the Martingale problem and the backward equation. So the Kolmogorov backward equation is this equation here, using the yeah, this duality relation here, this is a general result that if you have existence to solutions of the Martingale problem for somehow sufficiently many initial laws, then you get uniqueness of the solution to the Kolmogorov backward equation. And if you have existence of solutions to the Kolmogorov backward equation for sufficiently many initial conditions, then you get uniqueness for the Martingale problem. And this works here as well. Again, there's some involved infinite dimensional analysis in there, some more long computations, but at the end it also works more or less as you would think. Okay. Now I want to explain the new idea of Lucas, which is better than what we did before, and which removes most of these long computations which we needed there. And it's basically just after some brief computations, is basically just coming to abstract functional analysis. And so this here is a formulation which is not exactly how Lucas wrote it. It's based on an a priori estimate, which we actually had in our paper, but somehow we didn't realize what this would give us. And then Lucas realized what you can do with this. So let's not directly jump to the resolvent equation, but let's look at this at a regularized resolvent equation where we replace G by a truncated version. And somehow it has to be truncated in the good way so that things work, but let's not worry about that. Let's say it's now a bounded operator and it has all the nice properties of G. Satisfies the same estimates and so on. And let's consider the solution to this equation. Since Gm is now a bounded operator, this is no problem. You can solve this equation easily. Now let's take the solution and test it against psi to get a sort of energy estimate. Then using that psi is the right-hand side of this equation, we can plug in these guys here. And now we just split up. So this thing here, we integrate half of it to the other side. This gives us this term here. And then we remain with that part here. But now Gm is an anti-symmetric operator. So this is the same as minus Gm phi m. And of course, then, I mean, this thing is minus itself, so it has to be 0. So since Gm is anti-symmetric, if we have phi m, Gm phi m, it will be 0. And so this here is just the h1/2 0 norm squared of phi m. And now we can apply Young's inequality to split up these guys, and we get this less than 1/2 phi m squared plus 1/2 psi squared. This here is h0, 0, so we can of course bound it by h1/2 0. And then we pull this to the other side, multiply by 2, and we get this inequality. So we have an a priori estimate for the regularity of the solution, which didn't use anything except that the G is anti-symmetric operator. Right? That's all we used here. And this will automatically give us this bound. Okay, so what is this good for? Well, now we can get a subsequence which converges in a space of slightly worse regularity by a compactness argument. Here it's important that we have the torus. If we want to do things on R, things become a bit more complicated. And actually in this setting, we haven't worked out what would happen in an infinite volume. But on the torus, these spaces are compactly embedded and we can extract a convergent subsequence. And now these operators are bounded from certain spaces to certain other spaces. There's somehow a range of regularities you can plug into G, and for R0 you can basically plug in any regularity and you always lose one in the upper. In any case, 1/3 works for both of them, and any beta is for both of them, okay? And then we lose one in the upper and we lose one in the lower regularity. And so taking this convergent subsequence, we see that for its limit, we have that 1 minus L of phi is equal to, well, the limit of these guys. This is using the fact that these guys are bounded operators and that somehow this LMK will converge to L in a suitable sense. So we have this convergence here, but then this thing here is equal to psi for each k. So we have this identity here. And okay, the convergence in the middle is in a very bad topology. It's not in L2, it's somehow in a worse topology. But the right-hand side and the left-hand side of this identity don't depend on k, and they're both in L2. So we identified two L2 functions as elements in a worse space. But then they're also going to be equal as L2 functions, of course. So we have proven that we found a solution to the resolvent equation, now with a real operator here, with right-hand side psi. And using separability and some more work, you can find one subsequence such that this limit of these, so these are the corresponding phi and k's, exists for all psi. And so this then gives us a domain, right? So the domain of the operator is just A, so I write A psi for the limit along the subsequence of these guys. And so for any function psi in L2, L acting on A psi, we can write through 1 minus L. We want to apply 1 minus L to use this property here, no? And well, then we have to add this correction, and we see that this thing here will then just be psi, so together with the minus it becomes minus psi, and here we have A psi. But psi was in L2 and A psi is in L2, so this will always be in L2. Okay, so we have found a domain, and this time basically without computation. Now, once we have the domain and the operator, we can try to get a semigroup. And there's a nice version of the Hilly-Yoshida theorem, which is a bit easier to apply, which is called the Lummer-Phillips theorem, which says that on a Hilbert space, if you have a dissipative operator, so satisfying this estimate, such that the resolvent operator for lambda equal 1, or it has to be for some lambda positive, is surjective, then you automatically get that L is closed, its domain is dense, and it generates a contraction semigroup. And without going into...
is it possible to wrap it up in 2 minutes?
Yeah. Sorry. So these things, okay, these things are easy to check here. We have them, so we get a semigroup. And the point is, this is non-perturbative. I never used somehow a strong link between the linear and nonlinear operator. And it actually works in some supercritical regimes. So this works for a fractional version of the equation. If alpha is bigger than 1/2, the equation will be critical for alpha equals 3/4. So we can go beyond the critical regime. But in this case, somehow we don't have uniqueness of the semigroup. The operator, so to get the uniqueness of the semigroup, we would have to get the uniqueness of the domain, and this is not so clear. But we can do this and link also the semigroup with a stochastic process, with the Martingale problem, with energy solutions and everything, to everything we could do before, as long as we get a bit more regularity in the lower variable for the domain. And this was the second idea that Lucas had, which was very nice, to treat this operator as a perturbation of a I mean, it will somehow, we can treat it as an operator in this space, then it will not be anti-symmetric, but it will be a perturbation of an anti-symmetric operator. And then using perturbative theory for operators, we can still do something. And this works if alpha is bigger than 3/4, so this is subcritical, or if alpha is equal to 3/4 and we have a smallness condition. Smallness condition means you have to put an epsilon in front of the nonlinearity. Then you still get weak existence and uniqueness of solutions and so on. Okay, yeah, it works for some other equations and you can do some other things with it. But maybe with this, I just stop. Thanks.
Thank you very much. Let's go directly to Peter Friz, who will give the discussion. Hi, Peter.
Hi, everyone. Can you hear me?
Yes.
Okay, very good. So let me share my screen. So I hope you can see my beautiful software, which was written by the same person, or co-written by the same person who co-wrote the papers that Nicholas was talking about. So, well, let's jump straight into it. I'm not going to try to, drill into any details better than Nicholas has. This is impossible. But let me still rerun some of the main points here. So the running example here was the Perkowski equation, and as many of you know, this is basically the same as KPC, but you take one spatial derivative and then you get to the Perkowski equation. And if you do some formal computations, you get to this form of the generator, and that suffers from the fact that, if you think of the KPC equation having somehow spatial regularity similar to Brownian motion, and you take one spatial derivative, then you are not in the function world anymore, but in the distribution world. And so U square is a problem, and it's plain in your face. You have a problem here. And then the original ideas were to restrict these phi of U's to a certain cylindrical function of this type, and also that restrict to U of those processes that are absolutely continuous relative to the law of the noise, and that leads to this notion of energy solutions. And what was new here, or is new here, is that where Nicholas has been zooming in on this nature of the generator, in particular avoiding any previously used Kohl-Hopf transforms. And one of the ideas that comes into play is this move towards the resolvent equation. And I think in our community, we have seen this previously in the works by De La Rue Dille on the polymer meshes, but also there were other papers by I think it was Francesco Russo and co-workers that were cited. So there was some pre-rough, but so this can all be put together and be made work. Okay, that's it here. And so in the end of the day, what you get, well, okay, here's a big picture. You get a probabilistic Ito-type theory for classes of single SPDs. When you want to describe the domain of the generator, and this is what Nicholas has focused most of the talk, then some rough analysis tools come into play. The uniqueness of the Martingale problem uses duality arguments, and I think many people are excited about this outlook towards critical equations, and that was the very last part of his talk, of course. So I do have a question. I pre-asked that question to Nicholas this morning by email, so I already got a partial answer, which I guess he should repeat to the public here. So there's another weak way of constructing processes and SPD solutions based on Dirichlet forms, and some people have been very successful doing this, and that also has been made work for singular SPDs by the Zhu sisters in the 543 case, which is of course not at all the example that we have seen today. And so I will ask Nicholas to comment on this. But perhaps before we do this, I had a few extra thoughts that I wanted to bring into the game here, hopefully interesting to this audience, and that has to do with what I think is a related story. I mean, different, but yet related, that's about ongoing work, has been ongoing for a while with Antoine Hoquet and Coalet. And so it goes back to works in filtering theory, actually, years ago with Stan Grisson, Joshua Diel, Harald Oberhauser. And so if you strip away this filtering context, you're left with this type of equation here. And so if you ignore this final part here, so let's ignore this part here. Up. So let's ignore the red part here. This is a classical Ito SDE as you teach it to students. And you also teach them that you can compute the generator, et cetera, et cetera, et cetera. And if you add this thing here, and in this audience, I hope everyone has a feel what this X should be. This is a rough pass, of course. What else could it be? So it's temporally rough. It's not spatially rough. It's a good old rough pass. So if you add this rough stuff here, the first thing that you observe is, you can't use Ito theory, but also you can't use somehow 101 rough path theory to solve this equation, because this guy here is, in the language of Gubinelli, is not controlled. So this doesn't make sense really. So, okay, there's some song and dance, and there's a chapter, even a book with Martin on also called hybrid Ito rough differential equations, where you can have a look how we can do it in pedestrian ways. And basically we have a better way now doing it using stochastic steering. But in any case, if you take this formally, if you want to compute the generator, you realize immediately you can't do it because X is not differentiable. So what are you doing? And so the good thing is to look at Davis-style expansions. That gives you at least a way to think about it. So turns out this all leads to consistent calculus. And so if you take this X dot somehow with a grain of goodwill here, then there's also a mistake here that there should also be a dt here to make this precise and also formally. There's a rough Ito calculus, actually, it works pretty well. So if you build up the right context, then you have here, this is the usual part. Actually, sorry, the red part is what comes from rough. And so if you drop the red part, then again, this is basically the good old ether formula as you use it when you talk about Martingale problems in this setting here. And so of course, this thing here makes this a priori, you can't just plug it in at a fixed time t here. So in order to give meaning to the stuff, you should integrate up in time. And even then it's not a standard rough integral at all. You need some extended theory that deals with martingales and controlled rough paths at the same time. So here in a nutshell, there's a theorem that tells you that all this can be done, and I'm not going into any details. But the solution that you get here, because Brown motion has independent increments, is of course is a Markov process, and there's a martingale associated that you get in this usual way here. And so don't be fooled. This L here contains a lot of non-trivial rough stuff, and this dt integral here actually contains really a dx integral when you put in the correct form here. So that's the x dot together with the dt here becomes a rough integral. So don't, as I said, rough integration and either at the same time, and this is possible with correlated stochastic Zurich lemma, which I think is one of the major contributions to this field in the recent years. Now, as far as the test functions are concerned, it seems a bit dull here because this works when phi is nice enough and you need two derivatives or so. But if you move to the space-time process, and so you move to test functions that depend on y, so space and time, then it becomes much more interesting, because then suddenly you need somehow a controlled structure to make this work, and then you start seeing classes of test functions that are adapted to the noise, and that is morally much closer to what also Nicholas has shown us. Okay, time is running, but maybe I still have a minute. So once you have these SDEs in place, you take the expectation and then you come to PDEs. And in our case, when your L here hides this rough bit here, let's make this pretty red again. Then of course, this is a rough PDE. And if later in the day you plug in some Brown motion, then it's an SPDE here. That's the theme of the workshop, of course. So this is a linear equation, of course, but even so, the intrinsic existence uniqueness of these equations has kept quite a few people occupied, also Guminelli, Ismail, and others. And maybe one point I want to make is that if you look at this equation in some intrinsic sense, then uniqueness also relies on forward-backward duality. So that's another idea that seems to be, that's useful there, and it's useful here, and it's somehow related. And then finally, I want to come back to the theme of the workshop, SPDEs. And so linear SPDEs are fun, but nonlinear SPDEs are somehow more intriguing to many people. So there's a cool thing that has been made possible using stochastic Zurich, is that we can construct these hybrid solutions not only for some rough path, x and some Brown motion b, and some Markovian, state-dependent coefficients, but we can also let them be controlled. So alpha is exactly what you think it is. It's some adapted control process. So the usual tricks to construct hybrid ether rough equations using flow transformations, a flow transformation actually, within reason would work. But this trick that is explained in a book with Martin, where you construct a joint lift of b and x and then solve it as a big rough differential equation, that's going to fail here because of this pathwise dependence here. So with stochastic Zurich, you can do all this. And what happens when you start looking at the value function that if these are the underlying dynamics, you try to look at some, optimize some expected payoff, etc. Well, without rough paths, you get to HGB equations, and they are in general fully nonlinear. And so if you have this rough guy around here, then you have an HGB equation with rough noise. And so, essentially, this is exactly what Leon Souvenides wanted in '98, but they didn't have the tools to formulate it. So it was left somehow a bit on a formal level, and then they moved to these HGB equations, and within reason, within some structural restrictions, they made some progress there, but everything somehow pre-rough, and therefore they were quite limited. And so now you can actually not only make sense of this viscosity rough PDEs. There has been work in the last years on this, but also of the underlying modeling problem here. Now you can really formulate it in some intrinsic way without any tricks like flow transformations, which are somehow, they may work, but if you think of discrete approximation or something, at some point these transformations kill you. And so there are many benefits of a direct approach. So what I'm saying is this Markovian structure, and in this controlled Markovian structure with some ramifications, they lead us back full force to classes of nonlinear SPDEs. And these, I should also say, these SPDEs are within the scope or the world of rough paths, but they have nothing, as far as I can tell, as far as I know, they have nothing to do with anything that comes from the world of power-controlled distributions or regulatory structures. So if you're interested to judge, how do rough paths compare with these other things, then by the time you move rough paths into these types of PDEs, I think that the theories are completely disjoint, but I think both are important. So here we are. Thank you very much. I go back to the slide where I had the question for Nicholas, and I hope no one minded my digression to some related topic here. So here's a question for Nicholas.
Yeah, thanks very much for the nice discussion. Yeah, I think I also want to say something about this that doesn't have anything to do with the regularity structures and so on. But first about this. So in this work by Rongshan and Qiangshan, they construct this Dirichlet form, and through that construct an associated stochastic process for 543. Although for this they use the pathwise theory. So somehow this is on a technical level a difference, but then the process they obtain actually is an energy solution to the 543 equation. So it's a weak solution. The drift term is defined as a limit of drift term somehow. So like we had this discussion with this integral of L phi of u versus L phi of u not integrated in time. So it's the same thing there. You can only make sense of this time integral of L phi of u. And they also have the necessary energy estimates. And so they have all the technical conditions that we would have in energy solutions. But then the 543 measure is really a different level of difficulty than the white noise measure. So you cannot really do the same sort of calculus that we can do under the white noise measure. So it's not known how to prove uniqueness in law for these sort of energy solutions. For KPZ, or Burger's equation, there must be a Dirichlet form. And somehow, since we have the generator, in hindsight, we can write it even down. One could probably go directly through the Dirichlet form and construct also weakly unique solutions somehow by, using the kind of tools we have in a different way, but somehow I'm keeping track of the ideas we have there. It should work. Yeah, I've been asked that before, and probably I should do it or do it with someone at some point, but I haven't gotten around to doing that. Concerning this, these rough SDEs, they are in a sense very similar to this de la Rudiel kind of rough SDEs, right? So the only difference is that you have a distribution. If you write down the formal SDE with x dot and so, then you have a drift. If you interpret the rough path as a drift, which is a distribution in time. But in these works, we have a drift, which is a function of time, but then a distribution in space. But somehow conceptually, it's basically the same thing. It's just that the roughness sits somewhere else. And then this de la Rudiel stuff, and then Kanizawa-Chuk and all the later developments, they're of course sitting very much in para-control distributions and regularity structures. So I think there is a close connection. And yeah, this link to the nonlinear equations is very interesting. There may be a question to you. There is this, but I'm not sure if this was like a Hamilton-Jacobi-Bellman equation or a Hamilton-Jacobi equation. There are these results that you have this full dependence on the past in some of these nonlinear rough equations. That you somehow, like the noise, the solution at time t will somehow remember the whole history of the noise, and I cannot just let the equation run until time t and then restart and run until time t plus 1. But somehow to develop what's happening at time t plus 1, I must know the whole history of the solution until time t. Do you know what I'm talking about?
The closest interpretation of, or my interpretation of your question is that you have a dynamic programming principle because it's a control problem.
Yeah, exactly. So is this not a somehow?
So I mean,
or are these actually different models, or is there?
So perhaps first your question about HGB versus HGB. This is really HGB with the Bellman because of the presence of your thing. So that's a, you know, it's a second order equation channel. You have a dynamic programming principle. You also have to prove it. It doesn't come for free. And so for context, there was a quite popular paper in 2006 by Buktan and Ma on this stochastic. I said many other people were inspired by these, you know, ideas of Leon Stochanis. And so they had a situation where they had another set of Brownians, so independent Brownian motions. And so then they could basically, you know, make everything work with somehow stochastic calculus where they have somehow two different sources of noise. And establishing the dynamic programming principle was a huge pain and filled a 40-page paper in a prestigious journal. Yet measurability problems left and right. So all these evaporate here. This is surely an advantage. I mean, as far as the applications of the stuff goes, you know, there's easy critique, of course. X is a deterministic path, rough or not, it's deterministic. So whatever your optimal control will do, it will depend on the whole future of your path X. So if you don't like that feature, and in stochastic control, you know, if late in the day you want to put in some noise, you don't like that feature, then you have to do some extra work to penalize this, you know, look in the future. And that's actually possible, at least in some cases. And that goes back to ideas of Mark Davies many years ago, pre-Rough. And perhaps the one reference, if you're interested in this, would be a paper with Joshua Diehl and Paul Garcia a few years ago. I think it's called Stochastic Control with Rough Paths, where we implement this in some situations where we knew how to do it. And the people are, some people are working on this right now, including a guy at Zurich, and Andrew Allen is one of the names. So.
Thanks.
Okay, let's also open up the floor for anybody. Are there any questions from the audience? No, was there anything in the chat? Let's see. No, I think that was already answered. So in that case, let us give a round of applause for both the talk and the discussion.